set up from current slide. And just remind you of the two announcements I made all last week and probably the week before. The college transfer fair day coming up a week from Wednesday on the Birmingham West campus, 9:30 to 11:30. That's Wednesday, February 12th. That's the academic building, which is B Hall, on the Birmingham West campus. Then 2 weeks from this Thursday, on the 13th, we'll have them here, same time, 9:30 to 11:30. This building, Building A, they said campus cafeteria. My guess will be the rooms around the campus cafeteria because there's not really a lot of room in the cafeteria for everybody to be eating breakfast, lunch, and having this. So I imagine it's going to be in the faculty staff dining room mostly. But anyway, lots of schools have been invited, and so there should be a good representation there. Good time to make contact and check around. You're planning to go to Stanford, right?
Yeah.
Yeah, and they were invited. I assume they'll be here. And then the research experience for undergraduate for the University of Illinois, Arkansas, and Howard University. Wonderful program there. They pay you to go, $5,000 stipend, free housing, which I think includes food, and free airfare, one round trip there and back, getting it in. Okay, and lots of opportunities for learning. They pay you to do it. On this side, they said application deadline February 15th. That's the Saturday, I'm guessing. On this, it said the 17th, which is the next Monday, which I bet you is more accurate. If you want that information, you're welcome to look. Okay. Any questions on anything we've done so far? Okay. Where we left off last time, we're in 1.3, and we were just talking about different. Did I give you all the test? I didn't. Okay. I meant to have it run off this time, and I didn't, but I'll run it off before class is over, because nothing we're doing in 1.3 is going to add to anything that's on the test. Okay? I should have done that last time, and I just didn't have it done, but I'll have time after class this time. Okay, radioactive decay we're on Chapter 1, Introduction to Differential Equations. 1.3 is differential equations as mathematical models. And basically, anytime you hear anything talked about a rate is a derivative, a differential equation. So, radioactive decay. The nucleus of an atom consists of a combination of protons and neutrons. Many of those combinations are unstable. Not most of them, but several, okay? And when they are, that is, the atoms decay and transmute to atoms of other substances, and then they're said to be radioactive. The way they have to describe this is to model the phenomenon of radioactive decay. It is assumed that the rate, let me get my pen set up, okay, dA dt, that's the rate of radioactive decay, rate usually meaning time, so this is time, and this is the amount of the radioactive substance you have, that the radioactive decay, the rate of that, is proportional to, and we saw this before, the amount of the substance you have. Okay? So, of course, if you have just a little bit, the rate of decay is going to be pretty slow. If you have a bit more, a whole lot of it, the rate of decay will be quick because more of it's decaying. Actually, the rate is fairly constant. Well, to change the proportionality to an equality, it's dA dt is equal to Ka. And anytime you have proportional to, you can translate that to equal K, where K is a proportionality constant. Okay. If you have radioactive growth, decay is positive. If you have radioactive decay, if you have exponential growth is positive, exponential decay, then decay is negative. Okay. The example they gave, radon-222, I worked with this. For example, over time, highly radioactive radium-226, transmutes to a radioactive gas, radon, and that reaction, I'm going to write it like it's a chemical reaction, but this is a nuclear reaction. You have radium, Ra-226, I can't remember whether they write this top or bottom, I'll write it down here, 226 is going to be going to radon, Rn-222. Now something has to give there. These are atomic masses. What gives is an alpha particle, which is 4. Okay? Well, that's not the right way to express it, but that's what's going on. Now, what makes this one rather bizarre is radium is a solid found in the soil, okay? Not at large quantities, very, very, very minute quantities. However, some soils have more than others. And if you happen to have built your house over a soil that has high radium content, whether you knew it or not, it's never very high, but because this is radioactive, when you breathe in radioactive particles like alpha particles. Now, alpha particles, that's what that stands for. That's probably bad symbology. But those alpha particles will attach themselves because they're charged. And they'll attach themselves to dust particles, and you breathe those in, and they can go really deep into your lungs because those are tiny little particles. And it's confounded by smoking. So if you've got smoke in the air, whether it's people smoking cigarettes or some other type of tobacco, or just a smoky environment, then you could be breathing, and you've got radon around, that can be going deep into your lungs as well. The smoke is enough to get you, but then the radon can even be worse. Radium has a very slow half-life. However, radon has a 4-day half-life. So it hangs around. Now here's the difference. Radium's a solid. Radon is a gas. Okay? That means it escapes from the soil, and if the house happens to be built on top of a place that's high in radium, then all this radon gas can get into your house. It hangs around on average for 4 days. And it's constantly being replenished by other, because more radium down there. So it can build up quite high concentrations, and that can lead to health problems, mostly lung cancer. So we did a lot of study of radon gas, how to mitigate it, the houses that did have high radon gas. When I worked for Southern Research Institute, that was the main project that I was on there. So I did do some other things. All right. Now, if you recall from last week, we had Malthus's population study. The rate of population growth is proportional to the population, okay? Well, guess what? That's the same formula. It's just your K's may be very, very different quantities, some positive, negative, whatever. But a single differential equation can serve as a mathematical model for many different phenomena, like these right here. The next one, I'm not going to read all the words in here, but you can read those on yourself. Here's another one, Newton's law of cooling or warming. Now this one's a little different because of some differences in the characteristics. According to Newton's empirical law of cooling and warming, the rate at which the temperature of a body changes, now this is interesting, the rate at which temperature, which is capital T, but rate is with regard to time, that's little t. So this is dt dt. But there's capital T on top, little t on the bottom. Okay? That's proportional to not just the temperature, but the change in temperature with the ambient temperature, which they call T sub m. And that means the medium. Okay? So let's say that you take the turkey out of the oven and put it on the counter. The turkey is going to cool according to this rate. The temperature of the turkey is going to drop because the difference between the turkey temperature and the air temperature, the ambient temperature, is greater. Or if you take out an ice cube out of the freezer and put it on the shelf, it's going to come, and same deal, it's just one's dropping in temperature, one's rising in temperature. Okay, but that's it. And to get the, to make it an equality, again, change it proportional to times K, equal K. dt, dt, not understanding those are two T's. Capital T is temperature, little t is time, K times T minus Tm. And M they use as medium, I call it ambient. Okay? Now, this is sort of appropriate. Spread of a disease, especially a contagious disease, as in the coronavirus, okay? And boy, are they worried with this now. Now, if X of T denotes the number of people who have contracted the disease, okay, and Y of T is the number of people who have not. Okay. The rate at which the disease spreads, that's dx dt, okay, because x is always changing as a function of time, y is changing as a function of time, is proportional to the product. The number of encounters or interactions between these two groups. My writing stinks, okay? So how you say that is dx dt is equal to k, some proportionality constant, x times y. The interactions between the two. If you think about this, if only a very few people have the disease and a great number of your population does not, then that's going to proceed pretty slowly because, you know, there are only a few people who have it. Then once more people have it, and there's still quite a few people who haven't had it, the product is quite big. And then at some point, then the number of people who haven't had the disease may taper off pretty quickly, so then your rate slows down again. And that's typical of many diseases. Maybe slow starting at first, then once you recognize it's happening, that's when it's happening at a huge rate, and then it's very, very hard to stop. That basically is what happened several years ago with the SARS virus, Southeast Asian Respiratory Syndrome. They kind of tried to pretend that wasn't happening, and it was, and it got way out of control. This time, my wife's an epidemiologist, so I'm used to this kind of talk. This time she thinks they probably didn't know what it was. They just thought it was a bad cold or some type of pneumonia. And so they just were trying to treat it, and then finally realized it was already a pretty serious disease, but by that time, it was not at the slow rate, but at a much faster rate. So it's been much harder to control. Just like all the diseases like this, if they don't have vaccines, it's just going to grow. Now, a lot depends on the size of the proportionality concept. Something like probably the common cold probably has a moderate case factor, you know, whereas something like, trying to think what a really fast moving one is. Some of the flus really have a large K, and then some of the other things, I don't know, I would think something like leprosy or rabies or something would be pretty small because they're not very common, but they can be expressed. So it all depends on the size of that K and how soon you catch the disease before the X gets very big. The Y is always going to be pretty good size, but if you can catch it when the X is quite small, you have a lot better chance of containing. Okay. Now, in a very small population that you don't have very much mixing, then the people who have the disease and who don't have the disease, theirs are related to each other. If X plus Y is equal to N, that's the number of people in the population, then, see, what are they solving for? X, I think. X is equal to N minus Y, okay? So then, your rate would be, now they throw this extra 1 in there, and the reason is somebody has to bring the disease into the small population. So they put 1 more in, okay? Because if it was all a contained population, you couldn't be exposed anyway because no one had it. But one person comes in with it, then you have this. So this would be KX. No, I solved that wrong. I should have done it this way. Y is equal to N minus K, N minus X plus 1. And then this would be KX times X they do it N plus 1 minus X. Same thing, they just rearrange the order of it. And that would be their other, that is if you had a completely isolated population. Now that's what they're trying to do in China now. They're trying to contain everybody in that major city that got it, plus the surrounding communities that it spread to. Now they're trying to do the whole province, which is not going to be very likely, but it's already gotten out. The cat's out of the bag, you know, the cow's out of the barn, however you want to say this. It's in Thailand, it's in much of Southeast Asia. We have a few cases here. Now, well-equipped first world countries that have good health care and stuff, they can do a lot better job of treating it and containing it because we have facilities for that. But man, you get out into an environment like Thailand, which, in the big cities, they probably have really good health care. Out in the countryside, they probably have really, really poor health care and long distances travel to hospitals and things like this. So they may not have the facility to do a good job of treating and containing. So it's going to hit the worst people. Now, my wife was also saying that it looks like it's mostly adults, and it seems like maybe senior adults who have probably weakened immune system. And the other thing is, I think it's greatly exacerbated by smoking, because anything to do with the lungs and stuff, you're already stressing it with nicotine and the other carcinogens that are in tobacco, and then you bring in a virus like this, it's just going to go to town, And so So my older brother smokes. She said, I hope he doesn't get around anyone. But myself, I have a suppressed immune system because of my CLL, the leukemia. So she said, you need to watch it too, but not that we're going to be in contact with very many people from that portion of China. But to act like it's not going to get here, it is. Now, as springtime gets here, most of your viruses don't transmit as well then. It's when you're enclosed in cold weather environments, you're all in a house and you're sharing the same air. That's when it really tends to be worse. Okay, so those were spread of disease. And by the way, the classic descriptor of this would be when you have low infection, then rapid rise, and then when you get most people infected, it levels off again. This is your classic curve for many of your diseases. And like I say, the K is going to determine how steep this is or how gradual it is. It maybe comes up in just a very slow increasing and very slowly reaching the max. Okay. There you have a lot more time, opportunity to do something about it, and perhaps staying. But when they have something new like this, that there aren't any antivirals or any vaccines for it, things can get really out of control. Ebola, a few years ago, they had a couple of outbreaks. They've had them for several years. And again, those are usually in countries with very poor health care. And it just wreaks havoc. But the last one that was so severe, they did come up with some vaccination protocols and stuff like this that, knock on wood, you haven't seen many other outbreaks since then. That doesn't mean we won't, but they have developed some things that can work with it. The trouble with viruses, though, they adjust. If they start running into difficulties, they change their genetic structure and then overcome that. They are faster at it than we are faster at coming up with antivirals for it. So that's the bad news. Okay, let's move on to chemical reactions. Have you had chemistry already? Yeah, I thought you had something you said before. What's that? Yeah, I bet so. Titration curve. Okay, I hadn't thought about that. Yeah, it was very, very similar. Don't want to get into great detail, but they give an example here. The disintegration of radioactive substance governed by differential equations is a first-order reaction. In chemistry, a few reactions follow that same empirical law. If the molecules of substance A decompose into smaller molecules, natural assumption that the rate at which the decomposition takes place is proportional to the amount of the first substance that has not undergone conversion. That is, if X of T is the amount of a substance, I don't want to get into all this, but they show a couple of chemical equations here. You've got the book, so you can see those. See, the first of those, the conversion of T-butyl chloride, which is that first thing, CH3 CCl, and sodium hydroxide to go to butyl alcohol, I believe is what it's called. T-butyl alcohol and sodium chloride. Now, it's only the concentration of the T-butyl chloride that controls the rate of reaction. You got plenty of sodium hydroxide in the system, so that's not going to be a limiting factor. It's only going to be the amount of the T-butyl chloride that you have. and that's going to control. So then your dx dt, where x will be the concentration of the t-butyl chloride, will be proportional to or equal to K times the amount of t-butyl chloride that you have. Now, if this is your reaction, though, and they really, they don't do their chemistry well here, but in the reaction, this is a methyl chloride. It almost looks like the same type deal. The rate at which the reaction proceeds is proportional to the product of the remaining concentrations, CH3, the methyl chloride and the ammonium hydroxide. And they don't say why that's the case. And it's sort of irritating that they do. And here's the only thing I would suggest. You see, no. I don't think they do a good job of it. So I don't want to get into that. But anyway, that's the second order reaction. This is first order. Second order, when you have dx dt, that depends on the product of your things. Alpha minus x times beta minus x. Okay, where x is the concentration that you're trying to track, and you have two inputs, and they both are, you don't have an unlimited supply of one, and so that's the second order reaction. And again, their examples leave some, are not very satisfying, I'll put it that way. Okay. The next of these, and by the way, this one would probably be a curve more like a titration curve too, because you have two different things that are going on at the same time. Okay. So let's go off of this one and get to your mixtures. And you may remember questions like this in earlier math classes. If you're mixing two salt solutions with different concentrations, then you're going to have to come up with some answers. So the A here is the amount of salt that you're dealing with. And the amount of salt is changing over time by the input rate of salt minus the output rate of salt. Okay. So that would be Rn minus Ro. Amount in, or rate in minus the rate out. Now, depend on your things, and they give you some illustrations. The rate in would be your concentration of the inflow, the input rate of the brine, and that would be your input rate of salt, the product of those two. The solution being pumped out of the tank at the same rate would be dAdt. You don't know how much is in there for every 300 gallons of solvent, water, or whatever, times the output rate of 3 gallons per minute, which is the same. And that would give you an A of T, the output rate of salt that you don't know, and that's what you're looking for. And they come up with a formula such as this. I'm not going to go into great detail, where A is the amount of salt in there, dA dt plus 1 over 100 times A is equal to 6, where 6 is your rate out, I think it is. Yeah. But let's not get into that. But you see, there is an equation. Your independent or your dependent variable is your amount of salt. Your independent variable is the time, and your equation has this, the derivative of this, the amount of this, and then a constant on the other side. We will see several formulas with those kind of, or see several approaches that you solve that kind of an equation. So kind of hang on to the concept there. Now that's if you have the same input coming in, volume, as you have going out, but this is a higher concentration than this, or a lower concentration. It can go either way. In hydrodynamics, there is another thing, Torricelli's law, and since they mention him here, you can write on him if you choose to, either him, his law, how did he develop his law, or whatever, that states that the speed V at which water is going out of a hole at the bottom of a tank filled to a depth h is the same as the speed that a body, in this case a drop of water, would require free falling from a height h. In other words, the V is equal to the square root of 2gh, okay? Where h is the height of the depth of the tank, g is acceleration due to gravity, and the square root of 2 comes from characteristics of the equations. Okay. So the rate at which the volume is changing with respect to time would be minus a sub h. Now they haven't told you what, no, I'm sorry. Yeah, minus a sub h. I wrote b. Didn't mean to, it's just that it got connected. Okay. Times the square root of this 2gh. Okay. Since that's the volume. Now, this is a velocity, the square root of 2gh. This is an area. Well, velocity is distance per unit of time, right? So this is the area, which is distance times distance. So distance times distance times distance, that would be volume per unit of time. So this is volume per unit of time. So there is an equation that relates the amount that's coming out, I mean the area of the hole, sorry, area of the hole times the velocity. Now, and by the way, that's, yeah, there's a minus sign in front because the volume, the rate at which the volume is changing decreases as that the velocity decreases. So you have the minus sign there. The rate at which the velocity is happening is decreasing. Note here we're ignoring the possibility of friction in the hole. Okay, so that's, most of the time we are ignoring that. Okay. They throw another wrinkle into it. The area of the top of the water. I don't know why they threw that in there. Now, let's forget about this. Have you had physics, both electricity, magnetism, and mechanics? Okay. So you're probably familiar with this next one. You may or may not be. In series circuits, say again? Yeah. In series circuits, it was another class we did, Kirchhoff's second law, but that was dealing with only resistive circuits. This has inductors, resistors, and capacitors, and it's pretty interesting how they are related. An inductor which, by the way, is a coil, basically. And that's what they use to represent it. This is L. That's an inductor. L times the time rate of change of current. Okay? But current is the time rate of change of charge. So this would be L d2q dt squared. Okay? That's your inductor. In your resistor, which is like a light bulb or something like that, just the resistance there, I times R is equal to R times dq dt. Again, because current is time rate of change of charge. But a capacitor, on the other hand, which is this kind of a setup, okay? These are 2 parallel plates that build up charges. Then that's 1 over C times Q. So you see all 3 of these are related by the charge parameter, you might say. The capacitance by charge, just by the charge, resistance by the derivative of the charge, and inductance by the second derivative of the charge. So you can get some pretty, if you had all 3 of these elements in one circuit, then you would have L d 2q dt squared, I can't write, plus R times dq dt, which is current, plus 1 over C times Q. Those are all voltage drops across these elements, and this equals to your power, which is a function of time, your independent variable there. Not power, it's voltage. Okay, so it's an interesting illustration of how you can do this, and electronics just sets up so beautifully to follow these kind of rules.
And well, what I learned, they taught us the difference between like series circuit and parallel circuit.
Right, and these are series. This is a series circuit. Yeah.
Yeah, and like the series circuit, like each component they have like the same charge, like they share the same charge. You can kind of see it in the equation because the key is different, but like when you get to the voltages, like you have these different numbers that's basically making it like voltages.
Right. Yeah, these are voltage drops.
Yeah.
So all you're dealing with voltage here, but you're absolutely right. You have conservation of charge. You don't lose charge, you just use the energy from the charge. That's what voltage is joules per coulomb, energy per unit charge. So that kind of takes, even though charges show up here like crazy, that sort of takes them out of the picture because that is energy per unit charge. But these are voltage drops as you're going around. This is just one of Kirchhoff's law. The other Kirchhoff's law would be the junction law, which then the current, which is the rate of charge, is the amount coming in is the amount going out. So that's where your conservation of charge comes in those formulas. These are the voltage drops. So that's sort of why you can get away without, because your other formulas, it says Kirchhoff's second law. The first law is the junction law, which is that conservation of charge. So you hit it right. Okay. Much more common, this would be in mechanics, not electricity and magnetism. Why didn't they hit this one first? I don't know. Is Newton's laws of motion. And basically, if you have free fall, you have the mass times the acceleration is equal to the net force. Okay, and if the net force was just the force due to gravity, then that would be minus mg. Okay, but acceleration is d2s dt squared equal minus mg, and you could divide out the masses and have d2s over dt squared is equal to minus g. Okay? And that's what they're leading to there. Now, you can have initial value problem with this. If you know the initial position, s of 0, if you know the initial speed, s prime at 0, then you have an initial value problem. This is all assuming free fall. In other words, no other forces acting on the object. In other words, there's no air resistance. That's not realistic in most cases, but in a lot of cases you can ignore the air resistance. If you have a very small object that's not going very fast, it's not going to have a lot of resistance, okay? Especially if it's a fairly dense object. But if you do have that, Galileo had come up with this one. I think I'll put it on the new slide here, that m dv dt, that is the change of velocity per change of time. That's going to be connected with the resistance is equal to mg, that's the falling motion, minus kv. And that's related to the resistance as well. Mg is the free fall part, and kv is the resistance, the basically air resistance that depends on the velocity of the motion. Then you can get this in the terms of displacement by this. This would be m times d2s dt squared, because v is change of displacement with change of time, equal mg, now that's a constant, minus k dv dt. Oh, I'm sorry. K times ds dt. Because, like I said, velocity is time rate of change of displacement. Here you have derivative of velocity, which is the second time rate of change of displacement. And they just rearranged the order here to do m d2s dt squared plus k times ds dt is equal to mg. Okay. So again, just another way of rearranging order. And by the way, this force here is called viscous damping. Now, air is not very viscous, but it has some viscosity. If that was falling through honey, it would be very slow, okay, because it would be much more viscous. All right, there's suspended cable problems. I won't go into great detail. They do in the text a little bit of detail, but here's your differential equation that comes out of that. And it's a pretty simple seeming equation, but you got a lot involved with it. That the dy dx is proportional to the weight pulling down over the ti. Okay. They call it T1, okay, not TI. And you'd have to go and read the thing. That's the tension on the cables. So anyway, you get to several things, questions that will come up when we hit these differential equations. We won't do all of these, of course. We'll do more sort of cookbookish ones that are pretty easy to do. Some of these could get really hairy. Here are some of the questions that you'll run into. Does the differential equation actually have solutions? Okay, you've got to determine that. If a solution of the differential equation exists and satisfies an initial condition, is it the only solution that does? Are there some others hiding out there? What are some of the properties of the unknown solutions, if there are any? And what can we say about geometry of solution curves, if anything? Those are called qualitative analysis. Answering those kinds of questions, it's not really all that quantitative, just qualitative. Can we somehow approximate the values of an unknown solution? That is moving more toward numerical analysis. Okay? What can we actually come up with? Before you get any of that, we have what they call the analytical approach. And what I want to say is that you got to understand the analytic before you can really do a good job with either qualitative or numerical, though there are exceptions for that, I'm sure. In more precise terms, a dynamical system consists of a set of time-dependent variables, and those are often called the state variables. This one doesn't relate to that, the one I left on the board. Many of the others were, okay? The state of the system at any time t is the value of the state variable at that time, and those are quite often your initial and or sometimes boundary conditions. The solution of the initial value problem is then the response of the system, okay? So just a few points like that. And that pretty much finishes 1.3. Now, what we have here, a couple of things you can look at are problems 1 and 3. If those are in the back of the book, those are on the population dynamics. 5 is under Newton's law of cooling and warming. If it's in the back of the book, 7, the spread of disease technology. They're treating those as if those are the same, and sometimes I agree. But anyway, that's number 7. That's in the back. Number 9, mixture problem. I'll try to get those done. That's 9 or 11. Draining a tank, Torricelli's law, that was 13. Series circuit with inductors, resistors, and or possibly capacitors. Those are given there in 15. 17 is the falling bodies with air resistance. And then 19, Newton's second law and Hooke's law. We didn't mention Hooke's law, but it's there. 21 is single-stage rocketry, if you wanted to look at that one. 23, Newton's second law and universal gravitation. And then there's some other models there. If you want to take a look at them, if the answers are in the back, you can do that. Learning theory, infusion of a drug. Reflecting surface. That's, I think, pretty much, I think it's Stokes' law. That doesn't sound right. Usually the discussion problems don't have answers in the back. If any of these do, you can look at those as well. Usually they don't. Okay, and there's quite a few of them there. So let me get you and some other, if you want more practice exercises, the chapter 1 in review. Again, the odd number problems are in the back, so you could do number 1 if you wanted to, number 3, number 5, any of the odds 7 through 11, 13, 15, I don't know, 15 begins to be a little bit deeper kind of problem. You probably can still do it. It's a fairly easy one. But somewhere here, you usually get some of the more esoteric type problems. And I would, do as many of those as you find answers in the back. The odds are there, and if you can't find it, then you don't need to mess with it. Here's Vince, just when I was getting ready to go down and see the, excuse me. Where that's coming from. Is that right? You must have brought some in with you then. Okay. All right. I was just going to say I was thinking of going down and running off copies of the test, but do either of you have time constraints at the end of class? Okay, let's just wait till the end of class. I'll make copies. Let me just check and make sure I didn't have either myself or my work study student do that. No, I intended to, but didn't quite get it done. So anyway, we'll pick up the first test. I'll tell you that again when it comes out. Remember, we didn't solve any differential equations in Chapter 1. All we did was verify this, verify that, show this works, show that works. So there's no one and only one answer. Is you have to show that what they're saying is true. And so try to be sort of as concise with it and go through all the steps so I can follow what you're doing. Because basically you're going to be saying this equals that, which is what they give you to begin with. So show me that you can see how that happens. So Chapter 2 is first order differential equations. Now, 2.1 is more of this esoteric la stuff, okay? And it takes way too long for them to get through, but it is sort of important to have. Beginning with 2.2 through the end of the chapter, and this has 6 sections, so it's going to take a while to get through, that's where we learn to solve linear or first order differential equations. Some of them, 2.3, are linear, but not all of them are. Okay. So it says, before we can start, let's talk about some other behavioral things. How these solution curves behave, okay? And how they approach this, and I'm going, I think, to go to back a slide to have something like this. Some fundamental questions. We saw in section 1.2 that whenever you have an f of x and y and a partial of f with respect to y, and these satisfy certain continuity conditions, qualitative questions about the existence uniqueness can be answered. Okay? Blah, blah, blah. In this section, we'll see that there are other qualitative questions about the properties of solution. How does a solution behave near a certain point? Okay? Not a cut and dried answer, but sort of a what do we expect here? How does the solution behave as x goes to infinity? Well, we can't go out there, but how do you think it will? So here is the key. A key to what we're going to be doing here. A derivative dy dx, if you remember what that is, it's a differential function of some function y is equal to y of x. Okay? Now, this thing right here, for this function here, gives you the slope of tangent lines. That's what it is. Change of y over change of x. That gives you a slope of a tangent line. So if you know some values there, and this is sometimes called the slope function or the rate function, things like this, such as, here's a thing. If you had dy dx is equal to some function of x and y. And you'll see equations such as that. What that tells you is if you know an xy value that's on that grid there, then plug it in here to whatever this function is, and that tells you the slope at that point x and y. Okay? So if this point was right here, say, if this is the xy that you're dealing with, here's your x, there's your y. Okay? And if you know the function value of that, and this comes out being, I think they show here, something like 1.2. Okay? 1.2 is just going to be a little steeper than 1. There's going to be your derivative there. You know the value there, you know its derivative there, because if this just happened at that point to be 1.2. Now maybe over here it was 0. Well then that slope is going to be 0. That slope is this. If you have a lot of these in here, you can kind of follow the flow of where this differential equation is going for different values, okay? And then we're going to combine that with some other characteristics of it and get an idea of what these functions look like. Not solving them, but give you an idea of what some of their solutions may look like. What you're dealing with then, if you have that kind of a concept there, then what you have, this kind of thing is called a direction field. Especially if you fill in the much of the table. If you know the slopes, if you know this function here, this tells you the slope. If you know this function, plug in, this would be 3 minus 3. Plug in 3 for x, minus 3 for y. Plug it in, see what it is, 1.2. Plug in this one, which is minus 4, 0. Plug in a minus 4 here, 0 there. See what that slope is, okay? And do that all over the board, or at least in certain areas of the board, you can get an idea of what the function is doing at different times. Without time being in here at all, at different x's, okay? So that's what we mean. So what this could mean is that the curve is doing something like this there. So that is the slope of the tangent line there. So if you have a point up here where it seems like this is going to, and you see its slope is like this, then it's probably doing something like that. So you can kind of piece together what the flow might be if you started down here. If you started up here, the flow might be different, you know. So this just gives you a broad picture of what could be happening without knowing, say, an initial value. Or if you do know an initial value, maybe you can go from that. So, you don't have your text, at least not in here. So let me show you a couple of direction fields. Here's one, you see these represent slopes. The slope is fairly gradual here, almost 0, then increases, but then up here decreases, comes down. Here it goes down, up, and comes down again. Here it goes down, then comes up. So you see it has all different shapes at different values. Depending on what your initial condition was, where you are on that curve, that depends on what curve you're on, okay? It depends on where it goes. You also have something like this, and this may be example 1. So let's try example 1. Now, keep me posted on how time's going because I don't have my watch. The direction field for the differential equation, yeah, this is it, dy dx, that's pretty ugly writing, is equal to 0.2 xy. Now, I don't know if you remember this one, but we actually came up with a solution curve for this. I can't remember if we had initial values or not. But anyway, here is what your function is. Okay? Now, let's just pick some values here. When x is equal to 0, now where is x equals 0? Y-axis, okay? If x is equal to 0, all along the y-axis, these derivatives are 0. Right? Because if you have a 0 in here for x, your slope is 0. Well, you can fill in a lot of them right there, okay? And similarly, if y is 0, where are you? On the x-axis. And that also has slopes of 0. So here you got a bunch right here at the first. You can fill them all in without doing any major calculations. Okay? Okay, now you have to start making some. What if you're at the point 1, 1? Okay? Then this will be 0.2. So that slope will be very gradual here. Okay? 1 or 2, 1 would be twice that slope. Okay? Oh, that's probably too much. Okay? Something like that. 3, 1 would be a little bit more. 4, 1, you just keep on going. Then you could go up, you could go back, you could do something. But you see what those curves are doing differently. Okay? Now, they put these together. I don't want to draw them all in. I can't. I can't do a good job. Those are already pretty ugly. But here's what they have. See, notice on the axes, all the slopes are 0. Coming up here, the slopes make U-curves like that. Down here, they make U-curves like this. Okay? So, there's lots of different solutions for this, but you just have to figure out where you are. If you're anywhere up here, you're going to follow a curve like that. Anywhere down here, you're going to follow the opposite curve. Okay? So that would be the direction field for dy dx is equal to 0.2 xy. Okay? I don't know, it seems like these are pretty steep curves for what I'm seeing, but maybe they're right. Let's see. Yeah, because these are pretty high numbers. So. And then this would be joining certain ones of those. When C is greater than 0, you're up here. C less than 0, you're down here. Where C was an arbitrary coefficient. Okay? Okay. And that led to, and like I said, we did do this one before, and your solution curve here was, I thought I saw it, now I don't see it anymore. Yeah, here it is. Y is equal to, and we did this somewhere early in chapter 1, okay? Y is equal to C e to the 0.1 x squared. Okay. And I think we went through and did the verification of this. What's the derivative of this? 0.2 x c e to the 0.1 x squared. And then you go up there and plug that in. This for y, that for dy dx. And you see that does work, but that's where the C's came from. If C's are positive, you're in the upper part. C negative down here. C equals 0, of course, you're there. Y is equal to 0. Not very interesting function, but that would be C is equal to 0. It's what? It is time. All right, we'll pick up next time, speaking of time, with example 2 in this section. So let me go on and end this. Before I end it, I'll say I'm passing out the test today in case Peyton's listening at home, so you need to come by and pick up your first test. Okay? So let